Hello everyone. The topic of my research is effects of thermal bridges on the indoor thermal environment of passive buildings in cold and dry climate zone. Content. Abstract. The development of passive buildings have received more attention to achieving an energy saving and decarbonization of buildings. Controlling thermal bridges in the external envelope is considered the main technical way to achieve low-energy passive buildings. There are many climate zones in China. An in-depth study with different environments needs to be targeted to clarify the impact of thermal bridge treatment on passive buildings and special conditions. Therefore, this study conducts a transient simulation study on the design of thermal bridges for passive buildings in China's cold and dry climate zone. The transient simulation results show that the temperature trends of each envelope layer are different between the passive design and the conventional design at different time points. Because the passive design better handles the thermal bridge, it is more difficult for the external cold air to pass through the envelope's outer structure layer to the inner structure layer. In addition, compared to the conventional design conditions with thermal bridges, the indoor temperature rise rate under the passive design conditions is greater, and the energy consumption decreases faster. The subsequent study will be conducted under more realistic boundaries and initial conditions to provide general guidance for passive building design and heating operation strategies in China's cold and dry climate regions. In addition, experimental data will be considered to understand further the effects of different environment design conditions on the indoor thermal environment and energy consumption of passive buildings in cold and dry climate regions. Part 1. Introduction. The rapid development of China's economy has accelerated urbanization and the pursuit of the higher quality living environment, which has led to an increasing energy demand day by day. According to the China Building Energy Consumption Research Report 2020, the total building area in China was 67.1 billion square meters in 2018. The building energy consumption was nearly 1 billion tons of standard coal. Building carbon emissions were 2.1 billion tons of carbon dioxide. Against the background of the intensifying energy situation, building energy efficient and low energy buildings have gradually begun to receive attention from all sectors of society. In modern buildings, thermal bridges are inevitable due to difficulties in materials and complexity in geometric conditions. Thermal bridges can be classified into thermal bridges between walls and beams, thermal bridges between walls and floors, thermal bridges between walls and roofs and thermal roofs, and thermal bridges between walls and exterior windows according to their locations, shown in the figure 1. Most of the studies used experimental or simulation methods to investigate the local area where thermal bridges are generated to clarify the effect of thermal bridges on the envelope's thermal performance. Fewer studies have combined thermal performance and the indoor space to investigate the changes in thermal comfort conditions in the room after thermal bridging and the improvement effect of indoor thermal comfort after thermal bridging structure improvement. In addition, the use of simulation boundary conditions its less studies for the climate and indoor temperature characteristics in cold and dry climate zones. Therefore, this study mainly focuses on the climatic and interior design conditions in China's cold and dry areas. A numerical simulation method is applied to compare the effects of thermal bridges before and after improvements on the indoor thermal improvement environment of passive buildings. Part 2. Research Methodology. In this study, a room in the south orientation of a passive building in China's cold and dry climate was selected as a target building. The envelope structure of the actual project is shown in Table 1 through the research of the passive demonstration project in the cold and dry climates region of China. Based on the above basis, a geometric simulation model of the passive buildings was established as shown in Figure 2a. The geometric model is a two-dimensional model, which includes the interior space, each material layer of the envelope structure, and the refinement of the nodes prone to thermal bridges. Further, a geometric simulation model of the traditional building was also established for comparative study and analysis, as shown in Figure 2b. They reduce the influencing factors, the materials and the thickness of each material layer of the conventional building simulation. Geometric tree model are the same as those of the passive building simulation model. The main difference with the passive building is the intelligent method of the insulation layer at the joints of the outer envelope, the treatment at the nodes prone to thermal bridges. In particular, the radiant ceiling heating was adopted according to the actual project to keep the room temperature within the indoor comfortable temperature range. The water supply temperature is 30 during the heating season. To simplify the model, the inner surface of the roof was set as an ISO temperature boundary condition. Besides, a 20 mm insulation layer is added to the inner surface to slow down the temperature transmission from the internal surface to other roof layers. A structured grid was used for all computational domains since the geometry of the model in this study was regular. The control equations was solved numerically using the finite volume method. The simulation was performed with two-dimensional double precision and transient simulation, considering the thermal interior of the envelope. The influence of outdoor temperature on indoor temperature changes may not be reflected in a short period or a steady state condition. Therefore, the transient simulation was used and the simulation time was 24 hours. The outdoor meteorological parameters on the coldest day of Harbin in the severe cold and dry region are selected. Figure 3 shows the outdoor temperature and the solar radiation changes on the coldest day of Harbin. By adopting the above methods, we aim at learning the advantages of the passive building envelope design approach compared with the typical building envelope design approach and have an in-depth understanding of the temperature changes of each structure layer over time. In addition, the indoor environment is integrated to study the change of room thermal environment and energy demand under the passive thermal bridge design of the envelope structure. Part 3. Results and Discussion. Figure 4 shows the temperature change of the interior of the envelope with time at 4-hour intervals under passive building conditions. It illustrated the exterior wall surface temperature was as low as 30, but the heat was slowly transferred through the structure layer to the indoor environment. After 12 hours, the whole system reached thermal equilibrium. Therefore, the layers of the envelope formed a stable temperature. Stratification and the magnitude of the impact on the indoor environment was thermal decay. Figure 5 shows the temperature variation every 4 hours inside the envelope for the conventional design condition. For the conventional design, there were weak links between the exterior wall and the roof as well as the window. Lower outside temperatures are transferred more quickly through this thermal bridge locations to other structural layers of the envelope. Temperature of 3 points was selected to further compare the influence of external environment on the envelope layers and different designs. Figure 6 shows the location of these 3 points. Point 1 is at junction of exterior wall and roof. Point 2 is at the junction of exterior wall and window frame. Part 3 is at the junction of exterior wall and floor. The temperature change of the 3 points with temp and passive design and conventional design is shown in Figure 7. The temperature at these 3 points did not change much under the passive design condition. However, the temperature at these 3 points varied significantly with the outdoor environment, especially during the first 10 hours. Therefore, passive design could prevent external lower temperatures from transferring into the room through the enclosure structure. In addition, simulation results and passive and conventional design showed that the passive design could help to reduce the greater heat loss caused by thermal bridges and could further effectively prevent the cold outdoor air from transferring into the room in the cold and dry climate zone. As a result, the passive design could reduce the indoor heat demand. Furthermore, the indoor average temperature changes were measured to understand the influence of the outdoor environment on the indoor thermal environment and the different design conditions. Figure 9 shows the variation of indoor temperature over time and different design conditions. The indoor temperature gradually increased from the natural room temperature of 15 under the ceiling radiant between 8 and 12 o'clock. The indoor temperature increased faster due to intensity of external solar radiation affecting the room through the exterior windows. In addition, the indoor temperature rose more rapidly since the system had not reached thermal equilibrium in the first 12 hours. After 12 hours, the system gradually reached thermal stability. As a result, the indoor temperature changed slowly and only slightly fluctuate under the changing considering conditions of the outdoor environment. Figure 10 shows the changes in heating energy consumption under 24 hours. By comparing the energy consumption change of passive design and conventional design, it could be seen that the heating energy consumption of passive design decreased at a greater rate after 3 hours. When the system was balanced, the heating energy consumption and the passive design was about 0.8 smaller than that under the conventional design. Part 4. Summary. This study used numerical simulation methods to conduct a 24-hour transient study on the temperature distribution in the envelope structure, the indoor temperature change, and the heating energy demand under passive design and conventional design conditions in cold and dry areas. Under the set conditions of this study, the main results obtained are as follows. In the first 3 hours, the external cold air is transmitted through the outer structural layer of the envelope structure, and it has not had a significant impact on the indoor thermal environment. After 3 hours, the difference between the influence of the external cold air on the indoor thermal environment under the passive design and the conventional design gradually expanded. Compared to conventional design conditions, passive degree design conditions have a greater rate of indoor warming and a faster rate of energy reduction. When the system is balanced, the heating energy consumption under the passive design is about 0.8 less than the heating energy consumption under the conventional design. It shows that the passive design can play a better role in heat preservation and heat insulation. The enclosure structure has thermal inertia, and the heat transfer performance of different materials and design methods are also different. Therefore, follow-up studies need to conduct a longer transient simulation to understand further the effects of different envelope design conditions on the indoor thermal environment and the energy consumption of passive buildings in China's cold and dry climate regions. In addition, more realistic statistical boundaries and initial conditions from experimental investigations need to be used to verify the simulations accuracy. The experience learned can good passive building design and heating operations strategies in China's cold and dry areas. Thanks.